There's a moment when isolated decisions stop looking like coincidence and start looking like intention. For years, China's lunar missions appeared scattered, careful, quiet, easy to dismiss as routine scientific exploration, the kind that fills academic journals but rarely changes the world. But consider this one detail. In 2010, China mapped the lunar surface at 1 meter resolution in targeted regions. You do not need that kind of precision for inspiration. You need it for site selection, and that changes how you read everything that came after. Most space programs in history have been driven by one of two things: scientific curiosity or geopolitical momentum. Apollo was both a response to the Soviet Union and a genuine leap for human knowledge. But China's lunar program operates under a different logic entirely. It is not reactive. It is not symbolic. It is infrastructural. When China's National Space Administration began outlining its lunar ambitions in the early 2000s, the stated goals were modest by design: robotic exploration, scientific data collection, technology demonstration, phrases that don't attract alarm, phrases that don't generate headlines. But underneath that language, engineers and mission planners were doing something far more consequential. They were designing a system, not a single mission, a layered, interlocking architecture of spacecraft, landers, rovers, orbiters, and eventually, habitats. Each mission was not a standalone achievement. It was a node in a network that was still being assembled. Think of it like a chess player who has already seen the end game. Each piece placed not for its own value, but for what it enables 3 moves later. And the end game, as we now understand it, is permanent, self-sustaining human presence on the lunar surface, anchored to the most resource-rich location on the moon. But to understand why that matters, you need to understand how they got there. The Chang'e program, named after the Chinese moon goddess, began in 2007 with an orbiter. Chang'e 1 was not spectacular by modern standards, but it accomplished something essential: the first complete, high-resolution, 3-dimensional map of the lunar surface from a Chinese spacecraft, data that would inform every single mission that followed. Chang'e 2 arrived in 2010, 1-meter imaging resolution in targeted regions. At the time, this seemed like scientific thoroughness. In retrospect, it reads very differently. Then came Chang'e 3 in 2013, China's first successful soft landing on the moon. The U-2 rover moved across the Bay of Rainbows, a dark volcanic plain on the near side. It malfunctioned early, its wheels couldn't retract properly in the lunar cold, but it kept transmitting. For nearly 3 years, U-2 continued sending data, becoming the longest operating lunar rover at the time. And what it found beneath the surface suggested a volcanic history far more complex than existing. Models had assumed 9 distinct geological layers, evidence of multiple eruptions across hundreds of millions of years. The moon was not the dead, uniform rock scientists had long believed it to be. This is where everything started to shift. In January 2019, Chang'e 4 landed on the far side of the moon. No spacecraft had ever done this before. Not because it was impossible, because it required solving a fundamental problem. The far side never faces Earth, which means no direct radio contact is possible from the surface. China solved this by placing a relay satellite named Kuekiao at a gravitational equilibrium point beyond the moon, maintaining line of sight with both the lunar far side and Earth simultaneously. This was not a small engineering achievement. It was a prerequisite for everything that would come after. And the choice of landing site was not arbitrary. The Von Karman crater sits inside the South Pole Aitken Basin, the largest, deepest, and oldest impact crater in the entire solar system, approximately 2,500 kilometers across, 13 kilometers deep. The impact that created it was so violent it may have exposed material from the lunar mantle itself, rock that formed in the very first stages of the moon's history. The U-2 rover found something unexpected in the crater floor, a gel-like substance embedded in the regolith that scientists initially struggled to identify. After analysis, the working hypothesis pointed to impact melt glass, rock fused by the extraordinary heat of a meteorite strike. More importantly, spectrometer readings pointed to minerals consistent with mantle material, compounds that should not have been accessible from the surface without a basin-scale impact. The Farside mission was not just a technical first, it was a portal into the moon's interior history, and it pointed toward a deeper truth. The moon is geologically richer, more complex, and more varied than a century of observation had suggested. But that was only the beginning. By the time Chang'e 5 launched in November 2020, the mission architecture had evolved from exploration to extraction. The objective, land in the Rumker region, drill 2 meters into the surface, collect approximately 1.7 kilograms of lunar material, and return it to Earth. It succeeded on all counts. The samples were volcanic basalt, approximately 1.96 billion years old, far younger than any lunar sample previously studied. This shifted our understanding of how long the moon remained volcanically active, but the technical achievement may have been more significant than the scientific one. For the first time in 44 years, a robotic spacecraft had collected samples from another world and returned them to Earth. Autonomously, no human crew, no manual docking, the spacecraft rendezvoused in lunar orbit on its own, transferred the sample canister, and began the journey home. This was a capability demonstration, and this is the part most people miss. The same autonomous rendezvous and docking technology that works in lunar orbit also works, in principle, anywhere else in cislunar space. This is where the picture stops looking like science and starts looking like logistics. The lunar South Pole is unlike any other place in the inner solar system. Its geography creates something almost impossibly useful: peaks of eternal light and craters of eternal shadow, existing within short distances of each other. Some ridgelines receive sunlight for more than 80% of the lunar year, ideal for solar power generation. And inside the permanently shadowed craters just a few kilometers away, temperatures stay so consistently cold that water ice delivered by comets and asteroids billions of years ago has never sublimated. It is still there, waiting. Multiple missions from multiple agencies have confirmed this. India's Chandrayaan missions contributed critical data. NASA's L-Cross mission crashed an impactor into a shadowed crater and detected water vapor in the debris plume. More recently, the Stratospheric Observatory for Infrared Astronomy detected molecular water signatures even on sunlit parts of the surface, suggesting the water cycle on the moon is more widespread than previously understood. But here's where it changes. Detecting water is not the same as knowing how to use it. China's upcoming missions, Chang'e 6, 7, and 8, are specifically designed to move from detection to utilization. Chang'e 7, planned to land near the lunar South Pole, will carry a small flying probe designed to enter permanently shadowed regions and directly sample the ice deposits inside. It is one of the most technically ambitious robotic missions ever designed, and it is part of a sequence that leads somewhere very specific. Here is the detail that changes everything. Water is 2 atoms of hydrogen, 1 atom of oxygen, can be split through electrolysis into its component elements. Hydrogen and oxygen are the 2 most efficient chemical rocket propellants ever used. The main engines of the space shuttle burn them, so did the core stage of the Space Launch System. When you have water ice on the moon and solar power from nearby ridgelines, you have, in principle, a propellant manufacturing facility, not just for missions landing on or launching from the moon, for missions being refueled in lunar orbit before heading further out into the solar system. What this means is profound. The cost of launching mass from Earth is currently somewhere between $1,000 and $5,000 per kilogram, depending on the vehicle. Every kilogram of propellant a deep space mission carries from Earth represents a staggering expenditure just to escape gravity. But if you can manufacture that propellant at the lunar South Pole and transfer it to spacecraft in orbit, the economics of space exploration transform completely. The moon stops being a destination. It becomes a way station, a refueling depot, the first gas station between Earth and everything else. This is not a speculative concept. It is the explicit architectural logic behind the International Lunar Research Station, China's proposed permanent lunar base, and it is the reason every mission in the Chang'e sequence has been targeted one way or another at the South Polar region. Chang'e 8, planned for approximately 2028, will take the next step. Its mission profile includes not just landing and surface operations, but the first attempt to demonstrate in situ resource utilization, extracting materials from the lunar surface and using them to manufacture something on site. The specific target, testing 3-dimensional printing using lunar regolith. If successful, it means future construction on the moon does not need to import raw materials from Earth. The moon provides its own concrete. Chang'e 7 will also carry a multi-legged hopping robot, a craft capable of entering the steep walls of permanently shadowed craters, sampling ice, and then leaping back out to transmit its findings. Not a rover limited to flat terrain, a robot specifically engineered to navigate the geometry of shadowed craters, because that is where the most valuable resource is located. What emerges from this sequence is not a collection of science experiments, it is a coordinated system. Orbiters mapping in real time, landers testing extraction techniques, robots accessing previously unreachable locations, all of it feeding data back into the design of the permanent station that follows. The concept of building with lunar materials, what engineers call in situ resource utilization, or ISRU, sounds like science fiction until you realize the chemistry and physics have been understood for decades. Lunar regolith is rich in silicon, aluminum, iron, calcium, and oxygen, the same elements found in terrestrial construction materials. The moon does not lack building material, it lacks the processing infrastructure to turn that material into something useful, and that is precisely what the later Chang'e missions are designed to establish. If you can print a structural component using lunar soil, a wall panel, a radiation shield, a foundation block, you have broken the single most expensive constraint of long-duration space habitation. Every gram of material that does not need to be launched from Earth reduces mission cost, reduces launch mass, and reduces the extraordinary complexity of sustaining humans in space across months and years. A lunar base that builds itself from local materials is not just cheaper, it is fundamentally more permanent. This is the quiet revolution happening at the intersection of China's lunar science program and its engineering program. The science tells you where to go, the engineering tells you what to build when you get there, and the architecture, piece by piece, tells you that someone has already decided they are going to stay. In 2021, China and Russia jointly announced the International Lunar Research Station, a proposed permanent multifunction base at or near the lunar South Pole, open to international partners. The name is deliberate. By framing it as an international station from the beginning, China signals that it is not simply planting a flag, it is establishing a framework, a set of norms, partnerships, and technical standards that, if widely adopted, will define how humanity operates in cislunar space for generations. Several nations have already expressed interest in participating, not because they are necessarily aligned with China geopolitically, but because the station represents infrastructure that would otherwise take decades and trillions of dollars to build independently. The logic of joining an existing framework, even one built by a competitor, is not weakness, it is pragmatism. And it places China not just as a participant in humanity's return to the moon, but as the architect of the system that return operates within. This mirrors, in a striking way, what the United States did with the International Space Station in the 1990s, using a major infrastructure project to consolidate partnerships, establish technical dependencies, and shape the norms of human spaceflight. The difference is that the ISS orbits Earth. The International Lunar Research Station, if completed as planned, sits on the surface of another world, adjacent to the most strategically valuable natural resource beyond Earth's atmosphere. Step back for a moment and consider what this actually means, not in the language of geopolitics or national competition or the tired framing of a new space race. Consider it purely in terms of what becomes possible. A permanent base at the lunar South Pole with access to water ice means a continuous supply of propellant in cislunar space. Missions to Mars, to the asteroid belt, to the outer planets, provisioned from the moon rather than from Earth, the cost of deep space exploration drops by an order of magnitude. The economic model for space, always limited by the brutal physics of escaping Earth's gravity, fundamentally changes. The moon becomes the point of departure, not Earth. And whoever controls the logistics infrastructure at that point of departure, the fuel, the manufacturing, the communications relay, the landing sites, the processing facilities, does not merely participate in the emerging space economy. They define its terms. This is not alarmist. It is not a reason for fear. It is simply the logic of infrastructure. The nation or coalition that builds a port does not need to declare ownership of the ocean to shape who trades across it. The port itself is the power. We are living through a period that future historians will almost certainly mark as a turning point. Not because of any single mission, not because of any single discovery, but because of the convergence of capability, intent, and timing that is now unmistakably visible in mission plans, in budget documents, in engineering proposals that, taken together, look like a blueprint. The moon has always been close enough to see, but far enough to seem unreachable. For 50 years after Apollo, it sat in our sky as a monument to what was once possible. A reminder of a moment of human ambition that was never quite repeated. And then, quietly, without the drama of a countdown, something changed. Robots landed in places no robot had ever been. Samples came home from volcanic fields that rewrote planetary history. Relay satellites were placed at gravitational waypoints to enable communication across the far side. And the outline of a permanent station began to take shape. What is being built on the moon is not a symbol, it is a foundation. The question that will define the next century of human spacefaring is not whether a permanent lunar presence will exist, it is who will build it, on what terms, and with what vision for what comes after. The moon has always been there, but what humanity does with it, what we build, what we discover, what we establish as the first permanent toehold beyond Earth, that part of the story is still being written. And right now, one of its most consequential chapters is unfolding in the silence of the lunar South Pole, in the frozen darkness of craters that have not seen sunlight in billions of years. Something very large is beginning, and it starts with ice. If this kind of storytelling, the kind that goes beyond the headline and into what is actually being built, is what you want more of, then you already know what to do. There is much more ahead, and if this changed how you see the moon, leave a comment telling us what surprised you most. That conversation matters.